Welcome to a video where we're going to discuss hexadecimal and octal numbers, their bases, and I will tell you this is a good review for, or not a review, but a good thing to review before you start into this would be just the conversion from decimal numbers to binary and binary to decimal. If you remember what we would call as weighted multiplication or successive division. I don't want to take the time in the video to review that now, but that can be a good lead-in. So octal, though, are numbers that are base 8, and hexadecimal are numbers that are base 16. And we're using these because they are systems that can more efficiently communicate binary numbers on computer systems, you know, the same numbers with less digits. So octal, let's see, for place values is going to start really, it's just powers of 8 basically. So think like 8 to the 0, 8 to the first, 8 to the second, 8 to the third, etc. So that would be 1, 8, 64, 512, okay, and so on. So just powers of 8. Same thing would be with 16, which would be, you know, 16 to the 0, 16 to the first, 16 to the second. So we've got, you know, 1, 16, 256, and whatever 256 times 16 would be. Okay. All right. The method to convert from decimal back to these other methods is successive division. And if we're in binary or octal or hexadecimal and we're going back to decimal, we would use weighted multiplication. Alright, so we're going to do some examples, and hopefully through the examples this makes sense. Also, I want to tell you that there's a PowerPoint. For those of you that are in the DE course, there's a PowerPoint that goes along with this as well. This is just some guided notes that go with the PowerPoint, so we're just jumping right into the examples. But there is a lot more explanation and things should you want to take the time to look at that. But I thought for the video and the simplicity, you may just jump right into it. So converting from decimal number 94 base 10 to its octal equivalent, okay, we're going to use successive division. But because we're going to octal, we're going to take 94 and we are going to divide it by 8 since we're going to a base 8 number. So we're just going to go through and decide, you know, how many times does 8 go into 9? That's once. Just think regular subtraction. We're going to subtract. I'm going to bring down the 4. 8 goes into 14. One time. We're going to subtract, leaving a remainder of 6. We're not going to put a decimal and start bringing down zeros. Okay, so you do division and you get to where you have a remainder. Then you take the quotient from that answer, and that becomes the number we're going to divide by 8 this time. So we're going to do 8 divided by 11. 8 goes in one time. We're going to subtract 8, and we have a remainder of 3. Alright, you're going to continue to do this. So the quotient 1 goes in here until you have a number that's smaller than this, and you end up with, you know, 0 times. So 0 times 8, 0. Subtract, you get a remainder of 1. Okay, at that point the digits that you have are the digits for your octal number. The last one here being your most significant digit, and the first one being our least significant digit. So they're going to be written in reverse order. So we're going to have 1, then 3, and then 6, and that will become base 8. Okay? So the next example, same exact process, 189, we're just doing an extra example, divided by 8, 8 goes into 18 2 times, right, 2 times 18, or 2 times 8 is 16, subtract that from the 18, you get 2, that's not a remainder yet because we still have this other digit 9 to pull down, and 8 goes into 29 3 times, 3 times 8 is 24, subtract, and you have a remainder of 5. This is going to be your least significant digit. Okay, the quotient there, the 23, is what we're going to divide next. So 8 goes into 23 just 2 times. It gives you 16. You're going to subtract, and get a remainder of 7. And then the 2 is going to get divided by 8. 8 does not go into 2 at all. Subtract, and you get a remainder of 2. The 2 is our leading digit, so we have 2, and then the 7, and then the 5. And that is base 8. So we have converted from decimal to octal. All right, to go backwards, to go from octal to decimal, the next example, 136, we need to remember the value of each digit, or each place value. So this 6 is in the 8 to the 0 spot. Okay, the 3 is in the 8 to the 1 spot, and the 1 is in the 8 to the 2nd spot. Or in values, that's equal to 1, this is equal to 8, and this is equal to 64. So in the 1 spot, we have 6, that's like having 6 1s. We have 3 8s. This is the quantity of that value we have. The quantity of that value. So really we're just multiplying. So it's 6 times 1. Think of multiplying this row and this row. We have 3 times 8, and we have 1 times 64. You're going to get those products, and you're going to add them up. So let's see, 4 and 4 is 8, plus 6 is 14, carry your 1, and we're going to get 94. That is our decimal equivalent. So that would be base 10. Now, that just so happens you might have noticed that that was our example up here, and so we went from decimal to octal, and here we went back. So makes sense that we got the same answer. Okay, this one says convert octal again. It's the same thing. So we have 1 is in the 8 to the 2nd spot, the 3 is in the 8 to the 1st spot, and the 4 is in the 8 to the 0. So it's really 4 times 1, that's a value of 1, 3 times 8, and 1 times 64. So here we're going to add these up. 4, 4, and 4 is 12, and 8, 9, 92, base 10. Okay, to go from decimal to hexadecimal this time, hexadecimal, base 10, all right, we're going to use successive division again, but we're going to do it by dividing by 10. So we're going to have 94 being divided by, or sorry, I don't know why I said 10, 16. Hexadecimal is base 16. All right, so we're going to be asking ourselves, you know, how many times does 16 go into 94? And then the quotient, we're going to look at that. How many times does 16 go into that? So 16 goes into 94. Let's see, 5 times would be 80, and we're not going to be just shy of, right, we're only 14 away. So 5 times 16 is 80, subtract, and we're going to get 14. No more numbers to pull down, and that is less than 16. So we know we got the biggest quotient there. So we have a remainder of 14. Now, I jumped right into doing this, but there's a problem there. That's a 2-digit remainder. How are we going to put a 2-digit remainder in a single place value? So back on the front, you'll notice this chart, and I kind of skipped over it, but they give you our decimal numbers, the first 20 digits starting at 0, so 0 to 19, and they give us the equivalent binary, octal, and hexadecimal. And okay, in hexadecimal, each place value, we're counting in 16s, base 16. So the place value in this first place value, we should be able to go through 16 digits from 0 to 15. Okay, so we have to use a single digit for those. So once we get past 9, you see there's a problem, right? How do we do that? So we actually in hexadecimal start using letters. Okay, so the letter A is going to represent our decimal number of 10. B is going to represent our decimal number of 11. And so on. So C is 12, D is 13, E is 14, and F is 15. Once we get to there, we have captured 16. We have 16 different digits to take care of that first place value. After that, we will go ahead and put a 1 in the next place value. So that'll be in the 16th place value. And then repeat the count 0, 1, 2, 3. all the way up until we are in these letters again, A, B, C. So you can get eventually a 1A, a 1B, a 1C. So we are using letters now when we're in hexadecimal. So our remainder of 14 is going to get converted to the value E. So this is really remainder E. Okay, so now we're going to take 16 and divide by this quotient 5. 16 does not go into 5, so it's 0. 0 times 16 is 0. We subtract and we get 5. So we have a remainder 5. The last remainder is our most significant digit, so we're going to lead with that and go in reverse order. So we have 5, and then the next digit is E, and that is base 16, which can be written either with a 16 or it can be written with an H for hexadecimal. Alright, so the next one, we'll do this one. We have 429 base 10, or decimal form. Getting turned into hexadecimal, we're going to divide by 16. 16 going into 42 2 times. 2 times 16 is 32. Subtract, we get 10. Bring down a 9. Okay. 16 going into 109. I think 6 times is going to be it. 6 times 6 is 36, and the 6 times the 10 is 60. You get 96 if you add those up. So anyway, 96. I think we're just less than 16 away. 9 take away 6 is 3 and 1, so 13. So if 14 was E, 13 is going to be remainder D. Okay, and then we're going to take 16 and divide the previous quotient, 26. 16 will go into 26 one time. Subtract, you get 10. Now there's no more, so that's our remainder, right? But that is equal to A. That's the first 2-digit number, so that one's A. And then we're going to divide 1. So we keep going until our quotient is 0. That's the last time you have to divide. So 16 doesn't go into 1, so 0 times. You get a 0 product to subtract, and you get a remainder of 1. The last remainder is our most significant digit. So in reverse order, we've got 1, then we have A, and we have D. Base 16, or could be written 1ADH. Alright, next it says hexadecimal to decimal. Alright, this was a typo on these guided notes when they put the word octal in there. That should be hex. So that would be confusing if you don't catch that, or if you notice and I didn't mention it. So we're going to go hexadecimal to decimal. So going back to decimal, this is where we're going to use our weighted multiplication. So we've got our place values. We need to know what each place value is worth. So we have B, 2, and E. Okay, this place value is our 16 to the 0 place value, which is 1. The 2 is in the 16 to the 1 place value, which is equal to 16. And the B is in the 16 to the second place value, which is equal to 256. Okay, now the letters, we're trying to get back to decimal. We need to know what their decimal equivalents are. Okay, A is 10, remember, so B is really 11. E was 14. So the B means we have 11 256s. So we're going to say 11 times 256. And then we have 2 in the 16's place value. And we have E, or 14, in the 1's place. So we get 14, 32, and you need a calculator for this. 256 times 11, I already did it. I'm going to go reference. It was 2816. And then we add these up. So here we add up. We're going to get 12, 2, 3, 4, 5, 6, and 28. Base 10. All right, the next one, we only have 2 digits, 5 and A being in the ones place, right? 16 to the 0 or ones place. The 5 being in the 16 to the 1 or 16s place. So we have 5 16s, and we have A, which is 10 ones. 5 times 16 is 80. 10 times 1 is 10. Add those together, and we get a total of 90 base 10. Okay? Now we're going to go from octal to binary. All right, so we haven't covered that, right? So kind of octal to hex or octal to binary, any of those, and the PowerPoint does more examples of these last things. But here's the deal. The long way means you're going to go from, if you're not in decimal, you're going to go to decimal first. And then after you're in decimal, then you're going to convert from decimal back to the other one. So that just means we're going to use our successive division or weighted multiplication, kind of, each of those. There is a shortcut technique, and I really recommend those of you that are in the course I'm referring to, that you go and look at the PowerPoint and see a couple examples, etc. But we'll do both. Okay, so octal to decimal, we're going to do our successive division, we're going to divide by 8. Or, I'm sorry, we're in octal. 132. We're going to do our weighted multiplication. So this is 8 to the 0, 8 to the 1, 8 to the 2. So that's 1, 8, and 64. So we have 2 times 1, 3 times 8, and 1 times 64. Those products get added together to get our decimal number. So let's see, what do we get here? 90 base 10. Now that we're in base 10, alright, my monitor went to sleep and I had to go cut that out of the recording and start it. Thankfully I noticed that the screen went black. So I already started writing this out, so I'll just narrate, but we have to take this 90 now decimal and start converting it back to binary, and so we're dividing by 2 for binary base 2. And so I've got 2 goes into 90 45 times, goes in perfectly, we got a remainder 0. Then we divide the 45 by 2. 2 goes in 22 times, leaving a remainder of 1. Alright, then we divide the 22 by 2. That goes in perfectly 11 times, so remainder 0. Divide the 11 by 2, goes in 5 times, remainder 1. Divide the 5 by 2, goes in twice, remainder 1. I was trying to keep it all in one row. Divide 2 by 2, goes in perfectly 1 time, right? No remainder. But we keep going until we get a quotient of 0. So you got to go one more time. So that you're going to divide the 1 by 2, goes in 0 times, and you're going to get a remainder of 1. So there's kind of one more 1. So now these are in reverse order for our binary, that we're going to have the 1, 0, 1, 1, 0, 1, 0. And that's base 2. So that's the long way. Right, we had to take this octal and do weighted multiplication to get to decimal, and then take the decimal number and do our successive division to get to binary. The shortcut technique is really cool. Let's see what the example they asked us to do. It says convert hexadecimal to binary. So instead of going hex to decimal, hexadecimal to decimal, base 10, and then base 10 to binary, we can go straight from hexadecimal to binary and octal. Wondering if I've even done this. I think I did it. I didn't do the binary, but I did the octal. So, all right. So what we're gonna do, 8 and 6. I'm gonna kind of space these out. All right, A, remember, is equal to 10. We're simply going to communicate these two numbers in binary counts, okay, but with 4 digits. So 6 is in 4 digits of binary, okay. That's, remember, the 8s, the 4s, the 2s, the 1s. No 8s, 1 4, 1 2. There's 4 and 2 is 6, and no zeros. So there's 6 in a binary value. And then A, which is really 10, okay, again in 1, 2, 3, 4, we would need an 8, not a 4, and a 2. So it's 8, 4, 2, 1. So 8 and 2 gives us 10. We don't need a 1. And that actually is our binary number. So I did do it. I don't know why I didn't think I didn't, but that's your binary. And then if we want to go to octal, we take the binary count and we put it in groups of 3. Okay, and so why was this grouping of 4 or 3 that I just mentioned? Okay, is because in binary, these 4 digits, it takes 4 digits to make 16. So there's your hexadecimal. Okay, right? You get 16 place values, or 16 kind of values you can count with 4 places in binary. Octal, being 8, it takes 3 place values in binary to get to octal. So if we take 3 place values, here, I'll just go ahead and rewrite this underneath. So we had 1 0 1 0 0 1 1 0, and we group, starting from here the back, into groups of 3. I'm on the screen still. Okay, so there's a group of 3. That in binary gets me up to 8. And then the next group of 3, and then if you don't have a multiple of 3, what we do is we add leading zeros. So I need one more 0 to get us to a group of 3. And then we convert these octals, okay, into numbers, and that gives us our octal equivalent. So that's a 4 and that's a 2. So this is the number 6 in binary. So you're converting binary to the decimal equivalent. Okay, that's a 4 and that's a 2. The highest with an octal you can get with that group, 3 values in binary, is a 7, right? We're not going to get 8, we're going to get 0 through 7. So this 2, 4, and 6 is our octal equivalent. So 2, 4, 6, I'll put subscript 8. Make sure that's what I got when I did it before. Yep, there you go. So there are examples, and just kind of me writing it out for you so you can see it, that go along with the PowerPoint for those of you taking that DE course. Hope that helps.